So, why do we need to select features? Why can't we use all the features that we have in our hand, right? So this is because we can have some irrelevant features which are not contributing to our model, you know. So for example, you're trying to predict what is the test score, what is the, examination score of a particular student, and you have the data such as, whether that student can, let's say, play cricket or not. So okay, so that features won't help me, predicting the examination score. Okay, that is, those two are independent things. Someone can play cricket as well as do good in exam and so on, right? So those features cannot contribute well in our model, right? So those are the irrelevant features. Redundant features again. So for example, I gave this example in the first week. So for example, if you have a you're predicting the housing price, and you have in your feature, you have one as the size of the house, the length of the house, and then you have like the square feet of the house, which is basically length square, assuming that it's a square house. So you have length as well as length square in both the features in your model. So the one of the features is redundant, right? If you already have length, you don't need length square, right? It's already been taken care of. Limited training examples again. So you don't have, infinite training examples. You have some limited training examples, and you can only taking more features than the number of examples that you have is kind of a, ill conditioned problem, right? So again, if you don't know what is an ill conditioned problem, that's okay. But the fact is that, you cannot have, infinite number of training examples. So you need to have some limited training examples. So you need to have some limited features as well. Limited computational resources. More the features you include, more your computational power is required. So you don't have infinite computational power. So you want to minimize your features. So again, this is the graph, which is, if you increase your variables, so first your performance increases and then it decreases, right? So because you are including redundant features, irrelevant features, and so on, so that's why your performance will decrease. So we need to, select the features which are only relevant for our model, and that's why what we want to use. Okay. Now, there are two broad methods in which you can select your features. One is supervised and is unsupervised. So supervised is also called wrapper method. This is after you have built the model, then you select your features. Whereas unsupervised is something which you can do before even if you build your model. So in supervised, you can have like two methods. One is forward propagation and this backward propagation. So I think I explained briefly about these two methods in the first lecture when someone asked me a question on this. So forward propagation is something, so what happens is that, let's say you have 10 features, whereas you're predicting some target variable y. So what you do is that you choose the first feature first, okay? And then you fit your model, okay? And then you check the accuracy, error, and everything, right? And then what you do is, okay, now you choose the second feature. So you use the first two features together, then again you train your model and check the accuracy and everything, right? So now you see, okay, by adding the second feature, is my model giving a better output? And if it's giving a better output, how much better? Is it too much better or is it a little bit better? If it's a little bit better, then we can ignore the second variable. We can go on to the third variable and so on. That we can do. That is moving forward until we have exhausted all the list of features. And backward propagation is basically the opposite. First, we build our model on all the 10 features that we have, and then we remove one feature, one by one feature. And we see that, okay, by removing this feature, whether my model performance is increasing or decreasing, and if it's decreasing by how much. Okay, if it's decreasing by a significant amount, then okay, this is an important feature, we cannot remove it. Will try with separate other features, and we'll see which feature is more important, which is less important, and then we finally build the model with the best set of features that we have. Okay, is that fine? Okay. Moving to unsupervised learning. As I said, unsupervised learning is done before you build the model. So in the supervised learning, you have to build the model, but in unsupervised model learning, you don't have to build the model. As I said, these are some of the things that you can calculate. So for example, Pearson correlation. So this I extensively covered. This is the formula that I wrote. And again, I have calculated the Pearson correlation in the, in the this notebook. If you see, I'll go to it again. If you see, this is basically the correlation graph, right? So this means, as I said, I explained earlier, how is so this number 0.23, let's say, this number tells you how is glucose correlated with skin thickness. So if you see, okay, this is a very high correlation, then you can say that, okay, so let's see, let's choose one variable, okay. So this is, let's say, 0.65. So that means BMI is related to skin thickness. So these two variables are very highly correlated, BMI and skin thickness. So if these two variables are very highly correlated, you don't need to include both the variables in your data, right? You can do away with one of the variable. You can keep only one variable, right? You don't because your model will perform equally better with one of them in your feature set, right? Whereas the variables which are not very highly correlated, for example, BMI with pregnancies and so on, then in those cases, you need to keep both the variables, right? So that is the idea for Pearson correlation. And similarly for SNR ratio. So this is the formula for SNR ratio. Okay. This is the difference between the means of the two variables divided by the standard deviation between the two variables. So again, higher the SNR ratio, is higher the power of that variable to predict your. So yeah, again, I forgot to mention one thing. So in the Pearson correlation also, if I, go again to the heat map, so here you need to see also that how good is this glucose variable in predicting your outcome. So glucose is very high correlation with your target variable. So this is a very important variable. You must include this variable. Whereas some variables which has lower correlation, for example, this 0.17 correlation, diabetes pedigree function, this variable might be excluded because it has lower correlation, right? So you need to also check the correlation of your variables with the target variable. In that way, you can determine which is a better variable, which is not so good variable, and you need to keep the best variables to, in your model. And similarly, SNR ratio will check the SNR of glucose with the outcome. It will give you a different number, and again, higher the number, higher is the significance of that variable, and you should include variables with higher SNR and so on. So again, mu x is the mean of the variable, mu y is the mean of the outcome target variable, sigma x and sigma y are the standard deviations respectively. Right? So yeah, Niryogi. Correlation. Right. Right. If two variables, two features are very highly correlated, you can remove one of them because that would have redundant features. Yeah, Pritam. No, no. So I was saying, so there are two distinct things. Okay. So let me just go to it again. So there are two different things that I said. Okay. So this is the target variable. Outcome is your target variable. Okay. So one thing is you have to check is how two features are correlated with each other, right? So that means if, let's say, as I said, BMI is correlated with skin thickness, that means both the variables, both BMI and skin thickness, can predict, have same predicting power. So you can remove one of them. But then you see, like, you will see that if you want to see which one of them, let's say BMI and skin thickness, which one has higher predicting power in predicting the target variable, then you have to see the correlation of BMI with the target variable. So correlation of BMI with target value is 0.31, whereas correlation of skin thickness with outcome with your target value is 0.26. So then you see, okay, BMI can predict my target variable better than skin thickness. So you keep, okay, BMI I can keep and I can remove skin thickness. That way you can decide, right? Is that fine? Okay. So there are two things. One is the correlation within the features. One is the correlation with the uh, target variable, right? Okay.